Hi and welcome to this new video in which I'll introduce you to Kernel Memory, a library by Microsoft to implement retrieval augmented generation in C#. And even if the capabilities of the library are not comparable with Llama Index or LangChain written in Python that are more mature solution, this is a library that is promising and is written in C#. So if you're working with C# or in .NET environment, it's worth a try because you can easily integrate in your code with very, very little effort. As you can see from the code, I've simply created a service collection. This is a standard console application. I've created a service collection, and I'm going to call a function called create basic kernel memory builder that basically configure the kernel memory with all the options I need. To work, kernel memory need, first of all, an embedding library. And an embedding is a library that is capable of taking a piece of text and transform into a dense vector. And in this example, as you can see, I'm getting from environment variable, API key, and some information to use the Azure OpenAI config. So I'm using the Azure OpenAI services, and the version of embedding I'm using is the text embedding ADA002. It's not the most recent version of OpenAI, but this example is pretty old, so it still uses the old version. Now we have new version of embedding, but it is just simply, you can simply change the name of the deployment. This is all you need to do to configure the embedding part of kernel memory. That is absolutely needed to transform query and text into dense vector for vector retrieval. Then you have a chat config. The chat config is the configuration of the large language model that will be used to answer the user question. So the general working path for retrieval augmented generation is the user poses a question. The question is transformed with the embedding with the dense vector. Then you perform a search inside the vector database looking for all the pieces of information where the dense vector is more similar to the vector of the question, using Gaussian similarity usually, and then pass some of this result as with the question to a large language model and letting the large language model analyze the question, the piece of information retrieved from the database, and devise an answer if possible. So you need to configure a large language model. In this situation, I also take all the information from environments, but I'm using the OpenAI functionality exposed by Azure. So you need an API key, you need the name of the deployment, that can be GPT-3, GPT-4, the endpoint, and the API type, that is a chat complexion, and the key and everything you need to configure the service. And you also have a max token total that limits the number of tokens that the large language model can generate to generate the answer. Then I start creating the kernel memory builder passing the Azure OpenAI text generation and the Azure OpenAI text embedding generation, those previous two configurations. And now it's time, after this configuration that is common to all databases, it's time to configure the database I want to use to store the information and to do vector search. I've skipped the section on how I configure MongoDB because I want to start configuring a test database that is called Simple File Storage at Simple Vector DB. These are two databases that use local storage for storing data and for storing vectors. They are not absolutely meant to be used in production. They are included in the standard distribution of kernel memory. And the only purpose of these two version of databases is allowing you to test locally all the function you want, and clearly at a lower speed because the vector search is a brute force search. But it's indeed very useful even to explain how semantic kernel works. After I've built the kernel memory, you can build a memory serverless. And now you have the entry point for using all the services of kernel memory. Then I choose one document, and this is a book, Advanced API Security. I want to index, and I'm asking, it's a console application, I'm asking to the user if you want to index this document, because you will need to index only the first time, then it is stored in the database. And if the answer is yes, I call a simple function index document for indexing the document. The index document is really super simple because you just call the function import document async from the kernel memory object, passing the path of the document you want to import and a unique ID you want to use to identify the document. You can simply use the full path of the file for a simple example, or if you are if the data comes from the DB, you can have ID taken from the database. It's not important. And then I'm starting to await for get document status async, because importing a document is a process that involves a set of status. First of all, this is a PDF file. The PDF file, it's analyzed and text is extracted. Then text is subdivided into small chunks, and then all the chunks are passed to the embedding provider. So this is the OpenAI ADA embedding, and then the result is stored inside the vector database. So I'm going to simply sleep, waiting for the indexing to finish. Then I included in the sample some simple instruction, like the example on how you can get a reference of the storage database, and then from the storage database take a reference of one of the documents you have indexed. In this case, the first parameter is the name of the index. It's default because kernel memory allows you to index document in different indexes, so they are separated inside the vector engine. In the simple example, it is using the default index. And then I'm gonna simply using a loop where the user asks a question, and as you can see, the only function you need to use is the kernel memory ask async, that is performing the question to the large language model using the data stored inside the vector database as memory, and finally giving you a result. And so, as you can see, you've built a simple tool to ask question on one or more files information with very few lines of code. And now let's see how it works in practice. Now I've launched the program for the first time. All databases are empty, and so I'm answering yes to I want to index the document. So a part of fail that you are seeing is simply because the database is not initialized. And as you can see, it is going to generate text embedding. This is usually the slower part because extracting text from the PDF is fast. Subdividing into chunk is fast. Then you have a lot of chunk you need to pass through API, calling the OpenAI service in Azure, creating the embedding. You have a sort of throttling because you cannot do more than a certain number of requests per minute. You can increase in your Azure OpenAI configuration, but this is the moment in which you are spending the most time. But remember, this part, it's needed only when you first index a document, when you first index some text. After this, all the data will be stored inside those two databases. And as you can see, this is an entire book, and it does not needed a lot of time to generate all the data. We have simply waited for a bunch of seconds, and everything is inside the database. Now I'm proceed to create a question. Now I know that inside that book, there is a technique called complete mediation. And as an example, I'm performing the question. Can you please explain the technique called complete mediation? I just press enter, and it is going to ask to the vector database for a relevant piece of text that can answer the question. And it is answering me running grag prompt size. It gives me the size of the token used, and requesting max 300 token, and complete mediation is security principle that state that the system should validate access, blah, 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 blah. So you can see that with a very, very, very few lines of code, you were able to simply take a PDF file, index inside the vector database, and you are able to perform query on its content with very little effort, with code, all code in C#. So if you are a .NET developer, this is a good starting point to give your user this kind of functionalities. It is interesting to look at the local folder where I've configured the test database to use, because it gives you the idea on how kernel memory works internally. As you can see, I have two main folder. The first one is the storage DB, and the second one is the vector storage DB, because kernel memory uses two kind of databases. The first one, it's a pure object storage database, and it uses to store the PDF, the original document, the content, all the chunk, everything that is needed to everything that is a result of parsing, extracting, and analyzing the document. And this is a simple object storage. Then kernel memory needs a vector storage, and the vector storage is a complete different engine that is capable of storing vectors. So it's storing the dense vector resulting of the text embedding ADA functionalities of OpenAI, and the vector database must also support some sort of metadata filtering. So you have a vector, some sort of metadata. So kernel memory is able to query the vector engine with both query and dense vector retrieval, and also using some metadata filtering. And if you are looking at the content of those two databases, you will have a good insight on how a basic RAG structure is done. As you can see, inside the object storage database, you have one pipeline status JSON, and it's a simple JSON file where the kernel memory is gonna store all the information in it to understand how is going all the process of indexing a file. It's an internal file. We do not care about this, but as you can see, this kind of working allows for the pipeline to be to persist its state, so you can reindex a document or retrieve, start again indexing, and the pipeline knows what was done before. Then you have the full PDF file, and then you have the extract. The extract is the complete text extracted from the database, from the PDF file. So you can look at the quality of extracted text. Then the text is separated into chunks, because due to a limitation in large language model, you have a limited number of tokens you can use. So you usually do not pass the question of the user and the entire book content or the entire memory content, because it will not be feasible. Okay, I know that you can tell, hey, Gemini by Google has now 1 million or more token you can pass to the large language model. So probably you can easily pass several books inside a single prompt. But this is not usually a good idea, because it will gonna cost you money. So each time you call an API, OpenAI or Google API, you got billed by token you are using. So it is much more smarter and much more economic and more ecologic friendly, instead of using a lot of power making the large language model analyze a lot of text where the most part of the text is not pertinent to the answer. Try to find a much smarter way to take only the relevant part of your memory to pass to large language model. And that is why we are doing vector search. Then each piece of the entire text of the book is separated in pieces. And each piece will have a TXT file containing the part of text, the chunk of text that got extracted. So you can also see how the text is separated into chunk. And you have, for each of this chunk, a file that contains some information, some metadata, and all the vector. And as you can see, this is the ADA vector, and it's a vector that has about 1,500 dimensions, so it's pretty big. And all the rest of the text database is simply storing chunks, so it's not interesting. But it is interesting looking at how kernel memory works internally and how kernel memory analyze all the information to create a vector database. For vector storage, the situation is different, because the vector storage has not the purpose of storing information, but has the purpose of storing metadata and vector for creating, for allowing querying the data. And you can query the metadata for exact match, and you can query the vector for causing similarity. So the idea is, you see there are a lot of files with strange name, but it's some sort of internal ID used by the kernel memory. But as you can see, it's simply a JSON file in which you have a document ID, in which you have a file ID, in which you have the ID of the part, if you have the payload, the schema, and text. And you see, you have also the text, but also if you go down, you see the vector. Now, this is a test implementation of a vector database that is meant only to allow you to go up to speed with kernel memory. But it's not meant to be used in production, because when you perform a search on this vector database simply perform an in-memory Gaussian similarity for each vector. So it is using a brute force approach that is feasible if you have 1,000, 2, 3, maybe 10,000 of chunk. But when your number of piece of memory, it's like a million, this method is not going to work. So you need to use a real vector database like MongoDB Atlas, or some more dedicated vector database like Pinecone or Milvus or Elasticsearch. There are plenty of options out there, and Elasticsearch is growing and it's supporting more and more database as we speak. As an example, I've created a pull request for supporting MongoDB Atlas that is not still supported. And this concludes this video, in which I've showed you how easy it is to create, with a few lines of code, a very basic retrieval augmented generation pipeline using kernel memory. Now you can include these functionalities in your code, maybe to let your end user query its data, or you can use in combination with semantic kernel for creating agents that are capable of looking information in a long-term memory. And I know that if you compare the kernel memory with LangChain or Llama Index, clearly those two libraries have tons of option, more than kernel memory. But kernel memory is young, and if you just need some basic functionalities, it's really pretty good, and you can use with very few effort, directly integrated in your C# application, and without the needing of learning Python or other complexity. It's very simple to use, and as I told you, it worth a try. Bye-bye.